waiting. Yes, we have to wait, all right, because of this traffic, right? You take, maybe you take bus here. Okay, so we still wait for 1 or 2 more minutes before we start. All right, yeah, thanks. Okay, I just want to know about a few things. First of all, from yesterday's experience, do we need a break? All right, so I just want to have a second chance to let you voice out whether you need. I just learned from them, they have just come from a 3-hour lecture this morning, right? Then I said, I asked what module is that? It's engineering module. So I said engineers are good, all right? They can work for long hours, all right? For science, we also have 3-hour lectures, but for this module, it's only two times 2-hour slot, or 2 times 1.5 hours. All right. Yeah. Okay. Let's start something with more serious. I understand that yesterday you may have problems in accessing to Luminous, and I at least received some feedback. Want to have the IVLE still open for the whole semester. I tried, but first of all, IVLE, the existence of IVLE, to my knowledge, this will be the last semester. All right. Next semester, next academic year, I don't know how about special terms, but next academic year, there will not be any IVLE. So you have to get used to get your materials, your resources, all this from the Luminous. At least one thing you have to, but maybe not apply to you. Webcast is only available in Luminous. IVLE, you will see a note saying that go to Luminous to get your webcast. But since you are here, you may not need webcast. All right. Okay. So Luminous still. Okay. I tried to keep both, but Luminous seems to be going to be the dominant one, or maybe sort of official. All right. Okay. But I'm going to make some changes. The module code is ST2334, but there are 3 lecture groups. So I want to restrict the access to only this group of students who register for this group 1. So the code that you are going to access is ST2334_1. All right? So I don't know how many ST2334 modules in the Luminous. Oh, sorry. ST2334_1. So that referring to lecture group 1. So the materials only accessible by those students who registered for group 1. All right. So those will be all the lecture notes, announcement, or some other things will be available in this module. All right. I also forgot to mention yesterday about the tutorial. So the tutorial registration, I don't know when it starts. All right. But for exchange students, you cannot do online registrations. So maybe next week. Okay, you go to look at the schedule for all the tutorial groups. All right. Send me an email stating your preference, at least I think 5. 5 preference of 5 time slots for the tutorials. Only for those exchange students. If you can do online, don't send me email. And these 5 are in order of your preference. These are for the exchange students. They cannot do it online registration for the tutorial. All right. And what else? Yeah. I think for the time being, that's it. Okay. So let's start our lecture. So yesterday, We talk about operation of events. Okay. So we talk about union of events, intersection of events. All right, so today we continue. In fact, this should be finished yesterday. Okay, we talk about two events are equivalent. Equivalent, right? So if I have two events, A and B, equal. Oh, I can write A equal B. But in probability, what does it mean? What does it mean by two events are the same? So what it means is that the event A is a subset of a B, and event B is also a subset of A. By subset or contained, which means that all the elements in the set A also appears in the set or the event B. All, right, all the sample points in event A, all right, appears in the event B. Then we say that A is contained in B, or A is a subset of B. So only when A is a subset of B and B is a subset of A, then we say that A equals to B. So in that case, we say that these two events are equivalent. All right. So a simple example is this: like toss a die. So getting 1, 3, 5 is the same as getting getting a set with even numbers. So these two are considered as equivalent events. So here are some examples. I think you can read it yourself, but I want to highlight one point. Now this experiment, all right, throw a die first. So depends on the outcome. If it is an even number, then we toss the coin once. Yeah, so we toss the coin once if it's even number. So in other words, if you get a 2, then you will toss the coin once. So it can be head or tail. But if it's an odd number like 1, then you may get toss the coin 2 times. So this may be the possible outcomes. All right. Now, the point that I want to highlight is that, okay, look at this event. The event is described as that two tails occur. All right, 2 tails occur. It did not mention anything about what is the outcome of the first when you throw the die. But it's equivalent in this case. It's equivalent saying that the first outcome must be 1, 3, or 5. All right. It cannot be a 2, 4, or 6. Why? Because if it's 2, 4, or 6, then you can only toss the coin once. So my point is that sometimes when describe an event, because of the sample space, because of the S, okay, then it automatically or implicitly implies that the first outcome must be an odd number in this situation. So similarly, if you say that the even number shown on the die, then the outcome for the next must be only you toss the coin once. All right, it can be a head, can be a tail, but cannot toss the coin twice. All right, so you have to be aware of such situation. So you can read this yourself. So this is just another example to show how you operate the events. What is A intercept B? What is A complement intercept B complement, and so on. All right. All right. So let's start something new. Counting. It's quite interesting. I think since kindergarten, maybe primary school, we start learning how to multiply, how to add. All right. So multiplications. All right. Now we are in university. We also talk about multiplications. All right. So how we are going to use this one? Multiplication is very simple. 2 times 2 equals 4. 2 times 3 equals to 6, and so on. What does 2 times 3 mean? You see, at one point in Singapore, there's some argument, some discussions about 2 times 3 and 3 times 2. Are they the same? 2 times 3 and 3 times 2. Are they the same? Wow, a tricky question, right? From a mathematical point of view, they're the same. But from English point of view, what does 2 times 3 mean? It means a group of 3 appear twice. 3 times 2 means that a group of 2 appear 3 times. All right? So, if I have, let's say I have some cookies, 1, 2, 3 on this plate, 1, 2, 3 on this plate. So I have 2 plates, each has 3 cookies. So altogether I have 6 cookies. Well, 3 times 2 is like this. I have 3 plates, each one has 2. So, no matter how you do it, I still have 6 cookies. All right? So it makes no difference from mathematical point of view. But the underlying structure is a slightly different. One with only 2 groups or 2 plates. The other one is 3 groups. Now, so we know 2 times 3 and 3 times 2. It's easy. All right, how about this one? So if I have something like this, I have 3 plates. 2 plates with 2 and then 1 plate with 3. Can I multiply them? Why not? Because when you multiply, it means that you have groups. Each group has the same number of, in this example, cookies. Right now, I have 3 plates, 3 groups. They're not of the same. So what I can do is only I can multiply for those plates with equal number of cookies. So it can only have 2 plates with 2 cookies each. Then what happened to the others? Add. All right? So basically, multiplication is just to help you to do adding. Think of it. I have 2, 2, 2, 2. I have 100 groups. Each have 2. If I do the counting, I will do 1, 2, 3, 4, count up to 200. But now with multiplication, I know that 2 times 100, 100 times 2 will give me 200. So multiplication basically is doing some additions. Why I have to spend time to talk about this one? When you apply the multiplicative rule or addition rule in counting, in probability, or in combinatorics, you have to know whether the groups are the same. Same means that whether they have the same number of elements in it. So that's very important. All right? So what we are saying here is that, okay, if I do an operation, I have n1 ways to do it, all right? And each, this is important, each of these will have n2 ways. Okay, n1, n2, too complicated. Oh, by the way, if you find using n1, n2, these notations are too complicated, just use numbers. Let's say one operation has 3 ways to do it, and the second has 2 ways to do it. Then what we have is 1 way, 2 way, and 3 way for the first stage. And then each has 2. So altogether I have 3 times 2 because each way for each of the first operation I have 2 ways to do it. And they're all the same. So I can use multiplication rule. But if I say that, okay, sorry, the third way has only one possible way to do it, then you cannot apply this multiplicative rule. So you have to do the addition. You can only multiply those with those operations or those ways, those operations that with equal number of ways. Okay, so this is just another way to state the outcomes. So here is some example. So I have toss a die and also a coin. So I try to represent the outcome using these order pairs, x and y. All right? And x represent the outcome of a die, and y represent the outcome of the coin. So in other words, I can think of it as the first operation is the outcome of the die. So it's 1, 2, 3, 4, 5, 6. All right? And then each one I can have head or tail. So no matter what the outcome, I will toss the coin. So it is 2 outcomes. So altogether, it will be 6 times 2. So altogether, 12 elements. Now, I understand that you don't know this one. You can still write down all possible outcomes. But I warn you, you have to know how to apply this multiplication and addition rule, which we discuss later. All right? Instead of using brute force, don't try to use brute force. You must understand the mechanism of these rules and apply them correctly to get the answer. All right? So this case is 12. Of course, if you are asked, what are these 12 possible outcomes? Sorry, then you have to write it out. All right? Or you can use this to represent the sample space. All right? Okay. Now, this is a good example to illustrate the idea. So we have this community with 10 men. Each man has 3 sons. 3 sons. All right? So if we want to form a committee with father and son, a father and son, the son must come from that father. So how many ways that we can form? So we choose the father first. So how many possible fathers we can choose? 1 up to 10. All right. For each one, they have sons. So 1A, 1B, 1C. So 1A represents the first son from the first man. 1B, the second son from the first man, and so on. So altogether, there are 30 possible combinations, possible ways. All right? Choose the father first. And then for a father, then you can choose one of his 3 sons. So now here I have 2 questions for you. First of all, here, naturally, I start with father. So my question is, can I start with son? I choose son first. Can I? If I start with sons, how many sons are there? 30 sons. Once you pick the son, then what's the next? Choose a father. How many fathers does a son have? 1 only. So we still have 30. So if you do it right, you still get the same answer. There are 30 possible father and son pairs. The first one, I choose father first, 1 out of 10. But for each father, I can choose 1 of the 3 sons. All right? So, but if I start with son, I look at all the sons. I have 30 sons, so I choose the sons, 1 out of 30. But once you choose the son, automatically it implies that you choose his father. So that forms the pairs. All right? So it's still 30. Okay, my second question is like this. So what happens if 2 of the fathers, instead of have 3 sons, have 2 sons and 1 daughter? Form a father and son pairs. Okay, maybe too complicated. Drop the daughter. So just have 2 sons. 2 fathers have 2 sons. 8 fathers have 3 sons. So how many possible pairs that can we form? So I cannot straightly apply the multiplication rule. I have to separate into 2 different parts. First, the groups with 3 sons, because all these fathers have the same number of sons. The other one is a group of fathers with 2 sons. So in that case, I will have 8 fathers, each have 3 sons, and then 2 fathers with 2 sons, and I have to add them up. Okay? So the answer is different. So my point is that you can apply the multiplicative rule only to those with the same number of outcome in the next stage. All right? So in this case, you cannot have 10 times 3, but because 2 of the fathers do not have 3 sons. Okay, so this can be generalized into a more sequence. So instead of 2 stages, so the first stage you have N1 each. Remember, we are talking about each. That means every stage, each operation have the same number of outcomes. Okay? So altogether, you can think of it, how many ways get from here to here? So there are N1, N2, up to NR ways. So altogether, it will be N1 times N2 times N3 up to NR ways to reach from here to here. Okay, to appreciate what we're doing, let's look at some examples. So the first one is that we have these 5 numbers, 1, 2, 5, 6, 9. We want to form a 3-digit numbers. And we want to form not just 3-digit number. It has to be even number, even numbers. And only each digit can only use once. And so we want to find a way, how many ways that we can do form of 3-digit numbers, satisfy the conditions. 3-digit has to be even, and each digit can only use once. Are there any other conditions that we miss out? Remember, we cannot use 8, 4. They're not there. All right? So basically, you can only choose your numbers out of these 5 digits. 1, 2, 5, 6, 9. All right? So you have 3 digits, hundreds, tens, and units or ones place. All right? Now, when you try to figure it out, how many ways to do it, you have to first ask yourself, what are the constraints, or what are the conditions that we have to meet? The most important one is what? What is the most important condition that we have to meet? Because I already solved one, 3-digit. That's why I write 3 squares there. All right? Yes, even number. So that's the most important one. All right? Of course, there's another one is only used only once. All right? So we have to you have to meet these conditions first. So in order to meet this condition, we have to choose either 2 or 6 here. So the number of ways I'm not talking about digit. There are 2 ways to do it. So that's my first operation. I put 2 ways, 2 choices, 2 or 6 into it. After that, so I satisfy the most basic or primary constraint. Then the next one is that, should I fill in the hundreds or tens position? Does it matter? In this case, it doesn't matter. So you can use the next stage or the second operation is to fill up, let's say, hundreds. Okay, what I did here is to fill up the tens place. All right? So since I already used up 1, so there are only 4 digits remaining, so I have 4 ways to do it. All right? What are these 4 numbers or 4 digits that I can fill up in the tens place? It depends on what I take for the ones place. If I put up a 2, then the 4 left is 1, 5, 6, 9. If I fill up with 6, then the 4 left will be 1, 2, 5, 9. After that, then I fill up this one. So since I already filled up 2, only left with 3. All right, so now, should I multiply them? Can I multiply them? Yes, because for each operation, each stage, each operation, the same number of choices or outcomes that I can use. So in this case, it's 4 times 3 times 2. All right? Now, how about if we drop these conditions? No more conditions on use only once. All right? So we repeat again. So what what is the most important criteria that we have to meet? Even number. So I still fill 2 and 6. So 2 ways to fill the ones place. After that, then what I'm supposed to do? I can either fill up tens or hundreds. Would that make any difference? Shouldn't have any difference. So how many choices do I have for the tens place, let's say? Because I can use more than once. In other words, I can reuse the digits that I put in the ones place. So in that case, I have 5 here. And similarly, after I fill up these 2, I have also 5 choices here. All right? So the answer will be 5 times 5 times 2. Here's another example. Yeah, you know. So, multiple choice questions, 10 questions, 4 answers for each question. So how many possible ways of answering this test? So you can think of it. So should I write 4 boxes or 10 boxes? I have 2 numbers here, 4 and 10. So, so I consider 4 boxes and try to fill up the boxes, or if I have 10 boxes, each box supposed to represent the questions. If I have 4 boxes, then each one should be the choices, the answers. So which one should I use? 10 or 4? 10. All right? The questions is an individual, or consider as an operation. You choose, you pick up your answer. So for each operation, you have 4 choices. You have 4 choices. 10 of them. So each one, you have A, B, C, D. So it's 4. The next one, also 4 choices. I don't know whether, can I multiply them? So I have 4, so many choices. So I multiply them. You ask yourself, in the MCQ test, you choose A for question 1. All right? A, B, C, D should be equally likely if you don't know the answer. I have to stress you don't know the answer. If you know the answer, everything is fine. All right? Only one answer is correct. So what I mean is that for no matter what you choose for other questions, you still have 4 choices. So it's multiplication. You apply the multiplication rule. So it's 4 times 4, 10 times. So this is the answer. All right? Okay. Then how many ways you get all the answers correct? Huh? 1 only. All the answers. So the first question, you have only 1 answer. That are correct. Second question, 1 answer. And so on. So 1 times 1 times 1. So it's only 1. 1 way that you can get all the answer correct. So, is it hard? 1. So that means the chance that you get it correct is 1 over 4 to the power 10. Wow. What's 4 to the power 10? I don't know. 4 to the power 3 is 256. Wow. It's a big number. But don't worry. If you study, you will get all correct. This only applies to you don't know the answer and you guess the answer. All right? So the moral of the story is that please study. Okay. So the second part, how many of these answers are wrong? So, wrong answers. So, 3. Out of 4, 3 will be wrong. And this one also 3. So the answer is 3 to the power 10. All right? So what does it mean? It means that even if you don't know nothing, by guess, the chance of getting all wrong is, okay, not a small number, but there's a chance that you will still get some marks. All right? Because the difference between these 2 will be the ways that you will get some. 1, 2, or all of them correct. All right, so this, this is number, wow, 1 million. And answer all wrong, only 60,000. Wow. So in other words, I have roughly about 94% that I will got non-zero marks in this test. All right, if I don't study. But don't pay with your luck. Okay, I think example 3, you can read it yourself. 4, yes, you read it yourself. 5, basically it's just repeat what we just discussed in example 1. Now, maybe if I add, make a little bit more complicated, example 1 or this example, I add one more digit, add the 0 in the choice, and then you try to figure out what to do. And what are the answers? All right? Add one more, 0. That means, okay, maybe this is too complicated, then you go back to example 1, add a 0 as the choice. All right, and then see what are the answers. Yeah. The reason I put so many examples is just make sure to ensure that, yeah, if you can work out all these examples, all right, that means you know, you understand it. I'm not asking you to, for example, example 6, I'm not asking you to 4 multiply 3 multiply 5 multiply 4 and get the answer 240. And that's not what I want. I want you to understand why I can multiply 4 to 3 to 5 to 4. What does it mean? All right? So you have to understand it's the mechanism behind the multiplication rule. Okay. So this is a little bit more complicated. So, how many ways can 4 boys and 5 girls sit in a row if the boys and girls must alternate? All right? So, 4 and 5 make it easy. Why? Because you have to sit alternate. That means you must see something like this. Boy, girl, boy, girl. Things like this. All right? Now, because the number of boys is 1 less than the number of girls, so you have to start with the girl first. All right? Now, if you fill up like this, all right? No more boys. You cannot put a boy here. You still have 1 girl. Where to sit? Put it here. All right? Are there any other patterns that we can sit 4 boys and 5 girls, see in alternate seats? That's the only one. There are how many ways to do it? When we say how many ways, right? We treat each boy and each girl as separate individual. It's an identity. It's an individual, all right? So in other words, this B, all right? It's B, yes, boy. But it also means that there are 4 different boys. So how many ways can we sit? All right? So maybe boys, Alexander, okay. So these boys are different boys. These 5 girls are different girls. All right? So how many ways we can sit for the first one? 5 girls. So 5 ways, and so on. So that's how we do it. 5 ways to choose this. And then for the boy, choose 4. Although it did not say that you can use once only. Once you put a girl there, then the next girl position will be filled up by the remaining girls. So there are only 4 girls remaining. So there are only 4 choices for this position. Okay, so it's 5, 4, 4, 3, 3, 2, 2, 1, 1. All right, those are the number of possible choices for that position. Hey, can I choose to fit this position first? 5. Then next one, 4. Okay, then how about this one? 4 boys choose 1 already, so 3 left. Can I do that? Arbitrarily take the position. The answer at the end will be the same, but then can we do that? Of course we can. It doesn't matter. Because once you fill up the next one, the next empty seat that you're going to fill, you satisfy so long as satisfy the BG thing, then how many boys or girls left for you to choose? Then you just have to follow that procedure. All right? So I don't know whether you know about this notation. So it turned out to be something like 5 factorial times 4 factorials. This factorial, this exclamation mark, in mathematics, it means that it is a product, okay, of a number or okay, for this course, it's integer for product of integers, all right, such that it continue to multiply, but each time the factor is reduced by 1 until you reach 1. So 5 factorial means 5 times 4 times 3 times 2 times 1. 100 factorial means 100 times 99 times 98 until you reach 1. How about 1 factorial? 1. How about 0 factorial? Okay, what is 0 factorial? Okay, this one, unfortunately, you cannot follow. We can show that in order to be consistent, 0 factorial means 1. 0 factorials means 1. All right? We are going to use this quite frequently. Okay, additional principle. This is the real stuff. You just add. Count how many ways that you can do things. But they are in the same operation. Now, the multiplication rule applies to different operations. For each operation, there are so many ways in the next operation. While for addition rule, it applies to one operation. All right, so if you have n1 way to do it or n2 way to do it, so you add together, so it's n1 plus n2 ways to do things. So you can extend it to k possible procedures. So here is a simple example. So I want to go from my home to Orchard Road. Orchard Road is Singapore's famous shopping area. All right. So if you are new here, you should go to Orchard Road to see. All right. Okay. So there are 3 bus routes to go from my home to the Orchard Road and 2 MRT line to go from home to Orchard Road. So altogether, how many ways can I go from my home to Orchard Road? Now remember, each of these is to take you from home to MRT. You don't need to take a transfer. All right. So altogether, there are 5 possible ways to go from my home to Orchard Road. It's slightly different. If I need to go, I don't have a direct bus from my home to Orchard Road. I have to take MRT and bus, or bus, MRT, then bus, things like that. Then you cannot apply the addition rule. Here, each of these 3 bus routes directly from my home to MRT. All right? My home and Orchard Road. All right? So there are 3 buses, bus 1, bus 2, bus 3, and 2 MRT line. MRT 1 and MRT 2. All right, to go. So altogether there are 5 ways to go from my home to Orchard Road. So here is the 0 come back. This is example 1 with a 0. All right. Same question except we add a 0 here. All right. So now this makes the things more complicated. Why? Because when I consider the ones place, if I put a 0 there, then the rest of the integers, all right, so if I put 3 places, right, you see, I want you to understand why I have to consider separate cases. So at the end, I have to add up all the outcomes from case 1 and all the outcomes or possible ways in the case 2 to add this one together to get my answer. So because if I put a 0 here, the digit 0 here, then I can put any numbers, any of the remaining digits, so long as it satisfies the conditions. All right, use only once here. But if I don't put a 0 here, let's say I put a 2 here, 2 or 6, right? 2 or 6. Then how about the 0? The question is that the 0 cannot put in the hundredths place. Why I cannot put in the hundredths place? Do you consider 001 as a 3-digit number? No, it's 1-digit number. So you cannot put a 0 in the first, in hundredths place. That will not be a 3-digit number. So in other words, these two cases are slightly different. With a 0 in the ones place, you can continue to put any digits in the remaining 2 places and work out that. But with a non-zero there, then you have some problem. It's different from the previous case, because the 0 cannot put in the hundredths place. All right, so let's start with case A. 0 in the ones place. Then there are 4 choices here, and 5 choices. Okay, better make sure that it's a 3-digit number. So it's 5 and 4. It doesn't matter. 5, is it 5? Once I have 0, so the remaining is 5. After I put 1, there are only 4 left, so I put in the tens place. All right. You can also consider the tens place first and then put in the hundredths place. But if 0 is not used in the ones place, so then I can either put a 2 or 6 here. So there are 2 ways to do it for case B. All right, 2 ways. Either a 2 or a 6. All right. Now after that, should I consider to fill up the hundredths place, or should I fill up the tens place? Would that make any difference? You see, there's this criteria. You need a 3-digit number. So in other words, you must satisfy this one. So you make sure that the hundredths place cannot be a 0. So you have to fill up the hundredths place first. I mean, after you fill up the ones place. So now, how many digits remaining? You use 1 here, all right? 0, 1, 2, 5, 6, 9, right? So you use 1, let's say 2. You cannot use 0. There are only 4 choices here, all right? Now, but after you fill up this, then how many digits left? Still 4. Why? Because now I can include 0 in my choice. So there are 4 times 4 times 2. All right? Okay? So, you cannot consider this first. For this one, after you fill out 2, how many digits left? There will be 5 left. Is it? Okay, then, can I put any of these 5 in the tens place? Okay, you can fill up, but what happens if you fill up? Okay, you see the problems, why I have to stretch this one. Let's say I fill up a 2 here. Then if I consider this part, so I fill up 2, so I left with 5 choices. So can I pick any of these 5? If you say yes, okay. But then, what happened to the next one? The number of choices here depends on the outcome here. If it's not a 0, if I put a 0 here, then how many choices? I have 4. But if let's say I put a 1 here, then how many do I have? I use up 2, I use up 1, I cannot put a 0. Then I have only 3 choices instead of 4. So it makes it complicated. All right? So you don't want to do such things. So that's why I consider filling up the hundredths place first. So there's some kind of techniques. So you make sure that you do your order of filling up. If you do it correctly, it saves you a lot of work. Otherwise, it makes it complicated that you want to give up. All right? So here in this question, fill up the even number, so it's at ones place. The next one, fill up the hundreds place. Why? Because there's a zero here. Zero makes the things complicated. But if I fill up the hundreds place, ignoring the zero, then zero can be filled in the other places. Okay? So we must add these two together. Because why? Because with zero in the ones place or with a non-zero in the ones place, these two are mutually separate cases. So the outcome, the possible outcomes should be adding these two together. So I have zero in the ones place, there's so many ways. With non-zero in the ones place, I have so many ways. So I have to add these two together. Is that case 3? The case A with with a zero in the ones place. Case B with a non-zero in the ones place. Is that a third choice? A third scenario? We're talking about the ones place. So it's either a zero or non-zero. It covers every possibilities. Right? Okay. So altogether 52. So this is similar to the previous one, so you can get the part 1, but part 2, how many of these are greater than 420? Wow, 420. 420. 420. So what to do? Which one is more fundamental, more basic? I have 3 places. So which one should I fill up first? Which one should I fill up? All right? Should I fill up this number or this number? If I fill that ones place, how many possible choices? 0, 2, 4, 6. There's 4 possible choices. But if I put a 0 there or put a 2 there, will the subsequent number of operations the same? They're not the same. If you put a 0 here at the ones place, then you can fill any numbers in the remaining 2 digits. But while if you put a 2 there, then you have to worry about where the 0. Can I put a 0 in the hundreds place? I cannot. So you have to worry about that. So there are different situations. So I think, so that's one that you have to worry. Another one is that about this 420. So any number bigger than 420. So that will be, first of all, I have to consider, okay, let's see. Okay, this is a long question, right? Okay, the first questions, this follow from the previous example, so altogether you just add up. That is the possible numbers that you can form, even numbers. All right, now then the second part. All right, I start with the simplest one. Any number bigger than 420. So I start with 4 and 2, 402. All right? Greater than 420. So in other words, I try to fill up a 4, a 2. Then this number, okay, it has to, what are the numbers that I have? 0, 1, 2, 3, 4, 5, 6, all right? So I have 0, 1, 2, 3, 4, 5, 6. So 4 disappear, 2 disappear, all right? And any number greater than 420. So I can choose any of these numbers, 1, 2, 3, 4. So there are 4 choices. 0 is not there. Why 0 is not there? Okay, so it has to be greater or equal to greater than 420. So it does not include 420. So I have to have 4 of them. Okay, the next one, now we consider 4 here. Then in order, now, because it has to be bigger than 420, so it has to be a number, a digit greater than 2 in the tens place. So how many are there? All right, so you have only 3, 5, 6. So there are 3 choices. All right, where's 4? 4 already used here. All right, so after that, then you can put any numbers you want. So it's 3, 5, 6. All right, sorry, then it can be, after that, then after you use one more, there are only 5 left. So altogether there are 15. You see, sometimes you need this careful working. So I consider 420, 4, 2 in the hundreds and tens place, and then 4 in the hundreds place. Now I choose any numbers so long as it is greater than 4. So there are 2 choices, 5 and 6. 5 and 6. All right? Then the rest, I can choose any numbers I want to form a 3-digit number, greater than 420. Okay, so altogether, I add up all these possibilities. So that's the answer. 79 of the numbers are greater than 420. Okay, so what happens if I can use the digits more than once? All right, then, so this is the first one, no criteria. So I can put any of the 6 number, then 7 and 7. Because this one excluding 0. So you have 6 choices for this hundreds place. So altogether 294. Then if I want 3-digit odd numbers, then I make sure that the last digit is an odd number. So there are 3 ways, and then the rest will be 6 and 7. All right? So this one is make sure that it is 135. And this one, any of the 7. This one, any of the 7 except 0. So it's 6, 7 times 3. We can multiply because whatever we choose for that place, all right, the remaining operation will be the same no matter which digit you use for that place. So that's why we can multiply them. So even number is the same thing, all right? Then greater than 420. So same thing, except that now I have 4, 2. So how many choices here? Because I used 2 and 4. So I left with what? 6 of them now. Right? I use 4 and 2. But I can reuse it again. So I still can use this. The only thing that I cannot use 0. Why I cannot use 0? Because in that case you have a number 420. 420 is not greater than 420. It's equal to 420. So you exclude the 0. Then how about if I use 4, this one 4, then this one I can use 3, 4, 5, 6. So 4 choices, and then the remaining one, there will be 7. All right? So it's 1 times 4 times 7. And similarly for the others. So altogether 132 numbers. That is greater than 420. Okay. Permutations and combinations. But permutation basically is counting the number of ways to get certain arrangement. All right. So remember, permutation take into consideration the order. So you can think of it. If I have 3 digits, I try to arrange them to form a 3-digit number. Then I can have 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, and 3, 2, 1. 6 possible ways to arrange these 3 digits. But if I do not take into consideration the ordering, then to me it's just a set with 3 numbers. So there are only one. So you can see the difference between I just ignore the order, then I just have a set of 3 numbers. All right. So while if I take into consideration the order, then I have 6 possible arrangements. So permutation referring to arrange R objects out of a set of N objects. All right. So it's very simple. I try to arrange R objects. So I can consider I have R boxes, R places, and then each one I can fill up one of the N objects. So the first one, I can have N ways to choose. How about the second one? The second one, because I already put 1 here, so the second one is N minus 1. The next one, I've already used up 2, is N minus 2. So the number of ways is N times N minus 1 times N minus 2. How many ways can we choose for this one? Huh? The first one is N minus 1. The second one is N minus 2. So the R of 1 will be N minus R. Am I right? No. The first one is N, not N minus 1. It's N minus 0. So this one, N minus 1, R plus 1. Am I right? Right? N minus R plus 1. So basically, the number of ways to choose R objects, sorry, to permute R objects out of N objects. Right. So in particular, what happens if N equal to R? Or R equal to N? Then it will be N times N minus 1 times N minus 2 up to N minus N plus 1. So it's 1. It's 1. So the last one is 1. So here is 3 objects. So 6 ways to get it. How to get 6 ways? The first one, you have 3 choices, A, B, C. The second one, the remaining 2. The last one, the remaining 1. So it's 3 ways to choose for the first one, and 2 ways to choose for the second, and 1 for the third one. Okay, so this is called n factorial, right? And 0 factorial is equal to 1, 1 factorial equal to 1. All right? So, this is a notation used for permutation. What it means is that we are doing permutation. Remember, permutation means the order is being taken into consideration. And we are choosing R objects out of N objects to do the permutation. All right? So, you can think of it. We have 26 alphabets in English. So if I choose 3 letters from these 26 and then arrange them. So if I choose A, J, K, then I can arrange A, J, K, A, K, J, and so on. So the question is, how many ways can we form to take 3 alphabets from the 26 alphabets to arrange them? So the answer is very simple. P26, 26 is the number of objects that I can choose from, and choose 3. So follow from this, it will be 26 factorial over 23 factorial. Okay, what does this mean? I hope you don't have any problems with this. This simply saying that I have R ways to do I choose R objects out of N objects and then arrange them. So we just show that, okay, I can choose the first one, I have N choices, second one, N minus 1, third place, N minus 2, and so on. So the last one is N minus R minus 1. So I can continue to have N minus R minus, N minus R, then N minus R minus 1, N minus R minus 2, and so on. Continue until you reach 1. All right? Okay. Too complicated, I lost. So let's do it this way. Make it simple. 5 choose out of 5 objects. I choose 3 and then permute them. So according to what we just learned, it is 5 for the first place, 4 choices for the second place, and 3 choices for the third place. Then stop. This is the number of ways that we can do it. But I want to write it systematically. I can think of it, I multiply by 2 times 1, and then divide by 2 and 1. Right? I didn't do anything. But what is this part now? This is 5 factorial. And what is this part? 2 factorial. All right? So I can write this, choose, permute R objects out of N objects as N factorial over N minus R factorial. N minus R factorial. All right? So this will be a very useful formula for you to use to compute the permutations. But just a word of caution. How about if I choose 99 objects out of 100? So according to the formula, it will be 100 factorial over 100 minus 99, 1 factorial. Sorry, maybe just 2. This, just now the example is not good. So just choose 2 out of 100 and then permute them. How many ways can we do it? So according to the formula, it's 100 factorial over 100 minus 2 factorial, 98 factorial, right? Everything is fine at this point, up to this point. But then now I take out my calculator. I press 100 factorial, and then I say, error. I may be still in the old days. I don't know whether the calculator advanced to, you can get 100 factorial. If not, I can change to 1,000. So 1,000 factorial, sure you will not get the numbers. Blow up your calculator. All right? So my point is, you cannot apply the formula blindly. 100 factorial over 98 factorial. Wow, I have to get 100 factorial, which I cannot. Sorry, sir, I cannot do it. But if you understand the formula, basically it means that it's 100 times 99. Without a calculator, I know the answer. It's 9,900. So my point is, don't apply the formula blindly. So it's n factorial over n minus r factorial. So if sometimes you don't have to know what is the n factorial. You just try to simplify it using an alternative way. So in this example, it just means 100 times 99. All right? I know you are very familiar with your computer, all this software, but sometimes you understand a little bit thinking will help you go a little bit of, you don't have to waste time. Don't just rely totally on your machines, your calculator or your computer. All right, so this is why we define 0 factorials as 1. So look at it. If I follow from from what we just discussed, choose R objects out of N objects to permute is equal to N factorial over N minus R factorial. So if I choose N objects out of N to permute, then according to the formula, it will be something like this. But we know that this is equal to N factorial. So in order to make this correct, 0 factorial must be 1. Otherwise, you don't have this N factorial over 0 factorial equal to N factorial. This proof is not important now, but what I want you to remember is that 0 factorial is defined as 1. It's 1. 1 is a beautiful number. Yeah. Okay, so we apply the definitions. So find the number of all possible four-letter code words which all letters are different. Not very big, only 358,000. So that's why now your password, your password must be what? 10 digits, right? Including alphabets, including numeric, including special symbols, right? So to make sure that the number of ways, all right, will be very, 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 very huge. So that it's very difficult for you to guess. All right. But if just four-letter, especially if only four-digit code using numbers, using the 0 up to 9, then you have only 10,000 possible ways. So it's not very good way to construct the code. I mean, to use as a passcode. All right. There are 20 horses in a race. How many possible ways to arrange the first, second, and third place? So we have 20 horses. All right. So how many ways we get the arrangement for the first, second, and third place? So the first place, 20. Second place, after this horse got the first place, remaining 19 compete with the second place, and then 18. Right? So this is the way that we do it. But using the formula, n is 20, r is 3. So altogether, it will be 20 factorial over 17 factorial. So it's 6840. So in other words, if we have a horse race with 20 horses, all right, I don't know anything about these 20 horses, so I just bet on 3 horses in that order, like A, B, C horse in that order. Then the chance that I'm getting it correct is only 1 out of 6,840. All right, so it's very slim chance. So that's why it needs to do some homework. So that's why those interest in horse racing, to bet on horse racing, they do homework, some of them. Hey, even 4D, I believe people are also doing homeworks. How to do homeworks? Where's the tutorial or assignments? So some will look at the past record, all right, of the 4Ds, and then they try to guess what will be the numbers come out in the next draw. All right? I don't know if it works or not, but I believe it won't work. All right? Why it won't work? Hey, I studied, I spent hours to study the train. Why it doesn't work? Random event, okay. Because we believe it's independent. What it means is that the machine generate the 4 digits should not be affected by, it should not have any pattern. All right, they're independent or random. All right. But in a class of, let's say, 40 students, who will be the top in the class? That is not random. All right. So I just want you to understand that some are independent, random, so the outcome will not depend on any others. But some will. Okay. So we have 6 persons lined up to get on a bus. So how many ways? So the first one, 6 factorial ways to line up 6 persons. A, B, C, D, E, F. How to line up? It can be E in the first place and then B in the second place and so. So altogether there's 6 factorial ways. Now, if certain 3 persons insist of following each other. So now I already had it. Wow, you insisted 3 of them have to be together. So how do I put these 6 boxes? How to arrange these 6 boxes? But if you think of it, first of all, I put these 3 persons into one block. All right? Make it bigger. All right? Then, all right? I permute these 4 blocks, although one big, 3 small, but I treat them equally. So I permute them. All right? So, is that all? So, after you arrange them, this big block, let's say it's something like this, then you still have to permute within this big block. So in other words, I have to arrange these 4 objects. So in this case, 4 factorial. That is the way to arrange these 4 objects. While after each one, like, is something like this, for example. Then I still have ways to arrange within these 3. All right, 3 persons. So for each one of these 4 factorial arrangement, I still have 3 factorial, all right, to arrange them. Okay, so that's the number of ways that we do it. So it makes life easy if you understand the mechanism. So I consider these 3 groups, these 3 persons together. Okay, so we go the other way around. Now this time, 2 persons refuse to be together. Then what to do? 2 persons differently. So what to do? So we have to, that's why we need to know the complement. So we want to find out how many ways these 2 together, how many ways we can arrange these 2 persons together. Then we just subtract this number from the total number of arrangements. So that's the way that we do the things. All right, so the first one, 6 factorial. The second one, all right, is 4 factorial to permute these objects. And then each one, 3 factorial. So altogether, 1, 4, 4. Finally, 2 persons. So now I have this with 2 persons as one group. And then I still have 1, 2, 3, 4. So altogether, I have 5 objects here, 1 big, 4 small. To arrange them first, so there are 5 factorial ways to arrange them. After that, for each of this arrangement, I still have to permute these 2. So that altogether, 5 factorial times 2 factorial. Why I multiply 2 factorial? Because for each of the 5 factorial arrangement, the big block, we can rearrange within this big block. All right, so altogether there are 240. So refuse to together, so it's 480. So you have to understand, I want to get how many ways that 2 persons are not together. So instead of getting the answer directly, I work an easy way. Get the answer for how many ways 2 of them are together. Then subtract from the overall. All right? So that's this idea of complement is very useful. All right? Now we make lives more complicated. In a circle. Arrange the objects. They're distinct, but arrange in circle. Most commonly used example is to sit in a round table. All right? You're sitting, here is in a bench, all right? So the ordering is not, it has to be, you cannot do much. But while circle, you can think of it, if I have 4 persons, A, B, C, D, that is a one arrangement. So in this arrangement, A sit next with B and D. B and D. How about this arrangement? All right? Who sit next to A? It's still B and D. All right? In that case, what's the difference between this arrangement and this arrangement? No difference. No difference. All right? Unless you specify that A has to be in certain position. Otherwise, these are the same. So in other words, if you have 4 persons in this case, there's supposed to be 4 factorial arrangement. But unfortunately, or fortunately, there are some you cannot distinguish it. All right? So like A, B, C, D, A, B, C, D, A, B, C, D, and the last one, A, B, C, D. There are 4 of them. Basically, it's the position that A can occupy. They are considered as one, same permutation in a round table or arranged in a circular position. So I have to, this is, in this example, I suppose a 4 factorial arrangement, but for each of this one, not each, but among them, some are considered as the same. How many? 4. So altogether, there are 3 factorial arrangement. 3 factorial arrangement. All right? Okay. Maybe this one is hard to see. Let's do it with 3 persons. So what are the situations? You have A, B, C. A, B, C. Or A, C, B. A, C, B. All right? And what else? A, B, C, A, B, C. A, then what? A, B, C. Oh, this one is the same as this one. Okay, I better do it this way. A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. So these are the 6 if it's arranged in a straight line. Okay, now I put it together. So this A, B, C, all right, A, B, C is supposed to be just next to B, but if I put in a circle, C is next to A. All right, C is also next to A. C is, okay. If I put in a circle, it becomes A, B, C. So C is on the right-hand side of A. This one, B, A, C. C is on the left-hand side of A, so they are different. But while this one, this is A, you can write A, B, C. So C is also on the right-hand side. So these 2 arrangement is considered as the same. So what I'm trying to say is that if you arrange in a straight line, then you can see this n factorial. But once you arrange in circle, then some of them basically, now I consider who sit on my left, who sit on my right. Then you find that there are n of them basically means the same thing. All right, means the same thing. So you have to divide by n. So it becomes n minus 1 factorial. So this is the way to calculate it. So for 4 persons sit in a round table, so it will be 4 minus 1 factorial, so 6 ways. All right? Okay, now, when not all the objects are distinct, then we have a problem. But the problem, in fact, is not that hard. All right? Now, let's say I have n objects such that I have only k types. First type has n1, second type has n2, and the last has nk. All right? So, then the number of distinct permutation will be n factorial over n1 factorial, n2 factorial, and nk factorial. Why? Well, very difficult formula. But if you think of it like this, if you have n objects, what is the number of ways that you can get to arrange these n objects? So the answer is very obvious, n factorial. That's the numerator. But why we have to divide by n1 factorial? Think of it, if there are 2 objects that are the same, you cannot tell the difference. When you do the permutation, treat it as different, then you treat this as 2 or different objects. So let's say, think of it, A, B, C. So 3 distinct objects. All right? So altogether you have A, C, B, BAC, BCA, CAB, and CBA. All right? 6 different permutations. But now, if I change, sorry, I make a mistake. B is not B, B is in fact A. So I replace this by A. Replace this by A. Then how many arrangements are there? You can see that this one, AAC, is the same as this one. All right? And this one is this ACA. All right? ACA is this one. And finally, these 2 are the same. So, ACA. So there are only 3 distinct arrangements. So you can think of it. So what we just see AB, you can treat this AB as permutation. So you can have AB and BA. So now because we cannot tell the difference among them, so AB and BA becomes 1. Becomes 1 choice. All right? So that's why whenever they are the same, I have to divide the arrangement, the permutation among them. All right? So if your 2 of them are the same, so you divide by 2 factorial. If your 3 of them are the same, so you have to divide by 3 factorial. All right? So, okay. So let's look at this example. Okay. So we arrange 9 sockets for 2 blue, 4 yellow, and 3 red bulbs. So altogether there are 126. If you treat the bulbs, the light bulbs, as distinct object, then altogether there should be 9 factorial arrangement. But now the bulbs are only in groups of different colors, and there are 3 different colors. All right. So you have to divide this number of permutation by the number of groups of same colors. So 3 red. So I have to permute the 3 red and divide by 3 factorial. All right, because all these out of this 9 factorial arrangement, okay, some of them are the same because of the color. They are considered the same. So I have to divide 3 factorial because this 3 factorial is the number of ways that if you can treat it as different, treat these 3 red light bulbs as different, then you will be one of this 9 factorial. But now they are the same, so I have to divide it by 3 factorial. Okay, so example 2, straightforward. Example 3 also. All right. Okay, so now, combinations. Wow. Combinations is more popular ways of doing the counting than permutation. Because a lot of time we don't care about the ordering. We just want to see how many ways that we can choose things. All right. So we choose without regarding to the order. So that's called combinations. So we choose out of n objects, how many ways that we can choose our objects. All right. So we don't care about the ordering. We just take our objects out of n objects. So we denote it by NCR, or this one, choose R out of n. All right, so how to do it? For distinct, then the number of ways to choose R objects out of n objects is n factorial over R factorial over n minus R factorial. Wow, what is it, huh? Think of it like this. Okay, this tries to illustrate the idea of why we get that formula. I have 4 letters, A, B, C, D. All right? So I take 3 out of 4 letters. How many ways can I choose these 3 letters out of it? So now I do a permutation first. So this are the all possible ways to choose to permute 3 objects out of 4 objects. 3 objects out of 4 objects. Right? So first of all, we work out this. Choose 3 objects out of 4 objects. Choose 3 letters out of these 4 letters. All right? So this one is what? 4 times 3 times 2. So altogether 24. So these are 24. But if you notice that all these 6, all right, they are the same 3 letters, A, B, C, but just different order. All right? So if I don't care about the order, I only have A, B, C. And similarly for the others. So basically altogether I have only 4 distinct ways to choose 3 out of 4. All right? Now how do I know that? You can see that all these are the same permutation of these 3 letters. So I have to divide this 24 by the number of ways that I can permute. Okay, it's n factorial over r factorial, over n minus r factorial. So this is 4 factorial divided by 4 minus 3, 1 factorial, according to the formula that we discussed. All right? But now what I need to do is to count how many times that they are considered the same. So each one, they have 3 factorial because I choose 3 letters. I don't care about how they arrange. So how many ways that I can arrange these 3 letters? So they have 3 factorial. So I have to divide by 3 factorial. So that becomes the number of combinations. Or I divide by L factorial. So that's how we obtain the formula. Let me repeat it. The formula for the combination derived from the permutation. First of all, we choose R objects out of N objects to permute them. The number of ways will be N factorial. This is equal to N factorial over N minus R factorial. All right? Then for all this permutation, I have to consider how many ways that we consider as 1. So how many ways? R factorial ways. All right? Because each time you choose R letters or R objects, you permute them. But now I don't permute them. So how many ways can I permute R objects? I have to divide it. So choose R object of N objects will be PNR divided by R factorial. Choose R, arrange R objects of N objects, but among all this arrangement, I don't care about the order, so I have to divide a number, which is the number of permutations that you can have for the same R objects. So for same R objects, how many ways that you can arrange them? R factorial of them. So I have to divide it. So this is the formula. All right? And this is a very, very useful formula for calculating the combinations. All right? So altogether, there are, okay, so this is the how we derive it. This is more interesting. This is also called binomial coefficients. You know what is this, right? A plus B squared. You know this, right? A plus B cubed. A cubed plus 3A squared B plus 3AB squared plus B cubed. All right? You see this, all this you may not familiar with, but what we say is that, okay, I have 2 factors, A plus B and A plus B. So what I do, the multiplication, when I expand it, what I mean is that I take one component from the first bracket, this one. So it means that it's A plus B times A plus B. So I take A, and then I take A here, I got A squared. If I take A, I take a B, I got AB. If I take a B, take a A, I got BA. BB, I got B squared. Now, so basically, if I want to have A and B, what I do, I have to choose an A from the first one, then choose another one from B. So in other words, I need to have, okay, so I need to choose two. Out of these two, I must choose one so that I got an A. The rest, I won't choose A. So I got choose one out of two. How about this one? Forget about all this. So consider this one. How many A squared B there? A times B. What does it mean? It means that among these three factors, A plus B times A plus C times A plus B, among all these three factors, three objects, three factors, A plus B, A plus B, A plus B, I must choose two of them. So that for that choosing two, I must pick an A. And for the rest, I choose a B. Right? So how many of these three factors I choose two? How many ways can I choose it? So choose 2 out of 3. So choose 2 out of 3. And this means 3 factorial over 2 factorial, which means that 3. So I have 3, I can see that there are 3 factors which are A squared B. So that's why it is 3A squared B. All right? Now how many ways that we can get A cubed? Each one you must choose an A. So out of all these 3 factors, you must get A for all. So you choose 3 out of 3. So that means only one way. Every one you have to pick an A. All right. How many ways you don't have an A? That means B cubed. You don't choose any A from all these 3 factors. Choose 0 out of 3. Choose 0 out of 3. All right? So it is 1. What does this mean? 3 factorial over 3 factorial, 0 factorial. So it's 1. All right? Okay, I think I've run out of time. So these are mathematics, but also we have an interpretation of combination, how to choose things. So before we finish, just let you appreciate this. They're the same. Why they're the same? Mathematically, they're the same. The right-hand side or the left-hand side. This one, n factorial, n minus r factorial, and then n minus r factorial. They're the same thing. But from combinatorics point of view, think of it, you have n objects. I choose r objects. It's the same as I choose n minus r objects. All right? So let's say I have this class. I want 20% failure. So the other 80% they pass. All right? So how to choose them? So it's the same thing. I pick 20, let them fail. Or I pick 80 and let them pass. So what I mean is that you choose r out of n is the same as choose n minus r out of n. Right? You choose one. It's the same as you choose n minus r from the same group. Similarly, for the others, there's a similar definition, but we'll discuss it next week. All right, so we stop here. I believe your tutorial registration start end of this week, right? Go to do the online registration, and tutorial will start in week 3. Week 3.